Hi, good morning and welcome to this Morning Boost seminar. So my name is Martin Andersson and I'm a professor here at the Department of Chemistry and Chemical Engineering at Chalmers University of Technology. Today I will take the opportunity to present a little bit of our work here. And I work on materials, and specifically I develop new materials for biological applications. In our work we take inspiration from how things are being created in our environments. So we take ideas from biology and we try to mimic them in our laboratories. And specifically we are looking at trying to find solutions to our great global problems and challenges. So in this presentation I will give you 3 examples of strategies and ideas that we are using in the lab. So I will talk a little bit about making new materials that can decrease the use of antibiotics, because we have a global problem here that bacteria are becoming resistant to our used antibiotics. So we have to find new solutions to this. The second example is addressing the aging population. We are getting older and older, but we are using our bodies less and less. So there is a need to find spare parts or medical devices such as implants that can be used for a long time, that can keep us going and keep us fit. The third example that I want to address is about water. There is a shortage of fresh drinking water in the world. So how can we find new solutions to handle and purify water so we can make it accessible to everybody? So we are taking an approach here where we look at nature, we look at biology and see how things are being created. And we're also interested in utilization of this. So not only to take the ideas, make a material, but how we can create value in the society, how we can get our research out in benefit to the society in general. So the way that we do this is that we work as entrepreneurs and we create new companies to take our research into the society. So this is something that I also want to share with you this morning. So we take ideas from the outside and we bring them into the lab. So now I will take you into the lab and show you how it looks like. So follow me. Welcome to the lab. So now we are in a typical lab for material synthesis. So this is chemistry. So in chemistry we use atoms, ions and molecules, and we assemble them together in specific manners. And this is an approach that we call bottom-up. And this is essentially the same that is happening in biology. So here we are making materials, we are characterizing them at Chalmers and at other places around the world. And we then collaborate with people from biology, physics and medicine in order to tune them to function in applications. So now I will show you some examples of applications that we are working on. So the 3 examples that I would like to share with you today are new materials for improved implants, new materials to fight antibiotic resistance, new materials for water treatment. And in all these 3 examples, I will start by the motivation and describe the challenge that we are facing. Then I will move into how we take inspiration from nature, and then how we find new innovations in order to make up these or cope with these challenges. And in the end, I will focus on the utilization part. So how do we take use of these technologies in our society? So I will start by asking a question. So why do we work with implants? Why is this important? When I was a small kid, it was very common to see elderly people walking around with canes. Nowadays, you don't see these canes so often anymore. And the reason for this is due to that we have medical devices, such as implants. And the idea here is that we can use these implants instead And by doing so, we can stay active. We can play tennis even if we are 70 years old. And it's a fact that we are getting older and older, and also we are needing implant at a younger age. So there's a mismatch here. So we need to improve these implants in order to sustain active. The idea with implants as such is not a new thing. It's been around for a very, very long time. Here's just 3 examples, ranging back from 3,000 years old Chiron toe to making iron dental implants. And also the Incas, they used gold, for instance here illustrated in the center of this slide here, with a gold plate that has actually been osseointegrated or integrated with bone in the skull. Osseointegration is something that was actually coined here in Gothenburg by Per-Ingvar Brånemark. And he discovered that titanium can actually grow inside to bone, or bone can grow directly onto titanium. And he was an inventor himself, and he brought the idea of using this as dental implants. So you can say he was the father of the dental implant. And the same concept of growing into the jawbone also works for hips and knees. So what are then the problem here? Well, we are using more and more implants. They're common procedures. But to illustrate some of the issues, I have chosen to pick 2 slides here, or 2 graphs that you can see in this slide. So these are the number of total hip replacements in the US to the left, and the replacement or the lifetime risk of revision for total knee replacements to the right. And what you can tell from these graphs is that the life expectancies of these orthopedic implants are relatively short. And if you need a total knee replacement at a relatively early age, in the 50s or in the 60s, it would be a high chance or a high risk that you actually need to replace these knees. And if you get older and older, the risk increases. So there's a high need here trying to make up new materials that can prolong the lifetime of these implants. Now I go into the biomimetic part on this example. So I want to do this by starting looking at the structure of bone. So bone is a fascinating material. It's a composite. It contains a hard mineral, a calcium phosphate mineral, and proteins. And the proteins is soft. It's mostly collagen. And together they are making up a composite on the nanoscale. So these are very small features. And this makes bone a very strong material, still flexible and relatively lightweighted. Lots of people and researchers has looked into the bone and tried to figure out how bone is being made in our bodies. And what they come to the conclusion is that you form a type of soft template made of proteins, and you then deposit calcium phosphates in these onto these soft materials, and then are they mineralized, forming the bone structure as we know it. So what we have done in the lab is that we have tried to mimic this synthetic procedure. So we make soft scaffolds of synthetic collagen molecules into which we precipitate calcium phosphate. And when we do this, we will get a mineral particle that is very, very similar to the ones that you can find in our own skeleton. We have then taken these mineral particles and deposit them onto the surface of implants. And the concept and idea here is to make a synthetic material, such as titanium, into a material that resembles that of our own bones. And by doing this, we can actually reduce the healing time of these implants. And we can even make bioinert materials integratable. It will strengthen the integration and prolong the lifetime. And the technology also works on porous structures, which make it possible to get ingrowth of bone into porous scaffolds. So we have performed more than 30 preclinical trials on these surfaces using various types of implants. And here's one or an example to illustrate the effect of these particles onto the surface. In this specific example, we have a polymer implant. It's made out of polyether ether ketone, or PEEK for short. And this material is very popular for spinal implants, like spinal cages for fusion of the back. If you take this material, it's a plastic, it's quite hydrophobic and oily-like. It has very poor integration properties. And this you can see here to the left, where bone has been grown in close vicinity to the implant. But you can see there's a gap between the bone and the implant. So this illustrates clearly that there is not a true integration of the implant with the bone tissue. This compared to the right side here. This is the same type of implant, but with these bone-like nanoparticles deposited on its surface. And as you can see here, there's a distinct difference. You can see that the bone is directly anchored onto the implant surface. So this is a true integration termed osseointegration. And this will then lead to a higher stability of the implant. It will prolong the lifetime, and it will also probably avoid possible infections, because if you have a gap between the implant and the tissue, there might be a zone for growth of bacteria. So the idea and concepts was developed actually when I was a PhD student together with my friend Per Kjellin. So we were both PhD students when we kind of discovered this methodology of making these particles. We deposit them onto the surface of implants, and we can then show in studies that it was improving the implant. But it took almost 13 years from this idea to actually reach the market. So the first market introduction was on a dental implant, and it was through a Brazilian company. Today we are making about 100,000 implants per year, and what we can claim with these types of implant coatings is that they reduce the healing time with half. So this makes it good for the patients because they can start to use their implants much faster. We have a very high success rate of these implants, and we are also doing studies now showing that this type of surface coatings also helps when you want things to integrate in compromised bone. So this could be, for instance, patients suffering from diabetes. It can be smokers and so on. So they have a poorer success rates when it comes to the implants. But with this bone-like structure onto its surface, you can get almost as good integration as with existing implants in nice bone, so to say, which has not been compromised. Now we made this into a company called Biomimic, and Biomimic is in a growth phase right now because the technology not only work on dental implants, but we're also looking at the spine sector. So we have spinal implants on the market, and we are now looking at various types of introductions on orthopedic implants. And we are located in this Gothenburg area at the BioVenture hub at AstraZeneca. Moving on to the second example that I would like to share with you. This is about antibiotic resistance. So before antibiotics were discovered, more than 30% of all deaths was actually caused by bacterial infections. And as you know, an infection could be caused by a paper cut. So when Alexander Fleming discovered penicillin, it was a big breakthrough. It was called a miracle drug. But Alexander Fleming actually warned us. He said that if we don't use these new antibiotics in a good way, you might get resistant organisms. But we did not listen to him. We have overused antibiotics. We are misusing antibiotics. And this is causing a resistance to this miracle drug. Here's a kind of overview of how many deaths there are actually caused today by antibiotic-resistant bacteria. In the US and Europe together, this is causing about 70,000 people deaths. And worldwide, it's more than 1 million. But if we don't make a difference, if we don't change our usage of antibiotics, by the year of 2050, more people will actually be killed by these resistant strains as compared to cancer. So this is a big threat to humanity, and it's a big global problem. So what is the reason for this then? I said it's overusing antibiotics and misusing of antibiotics. And to illustrate this, you can see on this chart here, I realize there's lots of figures and names here, but on the top part of this graph, you can see the introduction of new antibiotics. But underneath here, you can also see when the first resistant strain of these antibiotics were identified. In the beginning, it took a few years before you find resistant bacteria, but if you go the timeline here, it took less than 1 year to find resistant bacteria to new antibiotics. And this is problematic because the industry see this, and if you develop a new drug which takes a lot of time, you need a lot of investment, and if it can only be used a year or less before you get resistance, there's a low driving force for developing new types of antibiotics. And this is what we see now. It's very, very few, I would say 0 antibiotics the last 20 years that has been introduced to the clinic. So what options do we have? Well, again, we can look at biology. We can see how are infections being treated by our own immune system. And in our own immune system, we have lots of cells that are helping us from invaders, such as bacteria. And these immune cells, they often produce short proteins, peptides, that has the function of being able to kill bacteria. So these are called antimicrobial peptides, or AMPs. And our immune cells produce these when they are under attack, and they can then eradicate the bacteria on site. So is this something we can utilize also as a treatment in the clinic? Well, I mean, the idea as such is good, and it works. However, there's a big challenge here. And the challenge is that these AMPs, these peptides, has a very low stability in contact with blood. So if you were to use them clinically, you have a very, very short window here when they are active. It could be seconds or just a few minutes. So then you have an administration problem because you need these AMPs to find the bacteria in a very, very short time. So this is the reason for why we don't see these antimicrobial peptides nowadays in the clinic. But there are ways to come about this, and this leads me to the innovation here. So what we have developed is a material onto which we can bind these antimicrobial peptides. And when we bind these peptides, meaning that they are totally immobilized, they keep their killing ability to bacteria. But at the same time, we also increase the stability. And this is due to that the enzymes that are actively degrading the peptides in the blood, they don't have the potential to bind to the peptides with their active sites. So we increase the stability from seconds, minutes, to days or weeks. So then it would be possible to use these types of materials in the clinical setting. So the first type of products or utilization of these peptides is on the treatment of wounds on the skin. So we have developed a soft hydrogel which is based on these antimicrobial peptides that when in contact with bacteria will eradicate the bacteria. In the same time, they are totally non-toxic and do not affect human cells. So just to show you and illustrate how well it works, I will show you these images here. So to the left here, you will see an image of green particles. These are alive bacterial cells. And on the right-hand side here, you can see these red, almost blob-like type of structures. So the green ones are bacteria that are thriving in a wound or on an ordinary wound patch. On the right-hand side here, you can see the same type of bacteria, but that had been in contact with this antimicrobial peptide wound patch instead. And the red indicate that they are dead. They're not longer alive. So this is a contact killing effect. So all bacteria that comes in contact with this material will be killed and cannot then cause an infection. Hence, we do not need to use antibiotics. So by having these types of technologies, we will reduce the use of antibiotics in the society, and we have one way of combating and fighting the increasing resistance. What's interesting with these antimicrobial peptides is that they don't only work against bacteria. They also work to eradicate viruses and fungi. And we have also initiated studies to look at the coronavirus, because what's unique with the coronavirus is that it's being covered by a lipid bilayer. And this is exactly the same type of target that we have for these antimicrobial peptides. So we have actually seen that the same type of technologies also works to combat the coronavirus. And we have been looking now into developing new materials and new treatments that can help us to stop spreading the current pandemic. So this is ongoing work. It seems to be working very fine. So it's a very exciting area to see if this biomimetic approach can also lower the risk of getting infected by the coronavirus. So this is some photographs of me and Saba and Anand. So we were the team that wanted to take these materials into the market and utilize them. So we started a company called Ampheria. And Ampheria is now in different clinical trials with these materials, and have shown that it works on the most common found bacteria in wounds and in infections, and that it actually also works against these strains that are resistant towards traditional bacteria, including these superbugs, where there's no antibiotic that is functioning at the time. So it gives a broad spectrum, and it's very effective. So we hope that we can introduce these on the wound patch market pretty soon. And we're also looking now at other types of possible applications for these materials. The third example that I would like to talk about has to do with water. So this is outside our bodies. So it's a fact that more than 2 billion people on the planet lack safe drinking water. And UN has decided that it's a human right to have access to safe drinking water. Since the population is increasing and we have a growing global impact on the environment, we need to find solutions to be able to get safe drinking water all around the globe. We also have an issue with increasing pollution of our oceans and lakes. For instance, microplastics, antibiotics, hormones, and other substances. So it's important for us to find out new innovations that can help us in this huge challenge. Again, looking at nature, nature has created devices that has fantastic possibilities. For instance, we have proteins that are located in the cell wall of almost all cells with one single purpose, and that is to transport water in and out of the cell. It can do this extremely selective and orthodox. So the only type of molecule is water. Not even ions can go through these pores or these channels. These proteins are called aquaporins. So an idea here is to borrow these aquaporins from the cell membrane and make devices out of them. So we want to take use of these proteins, and how the way we make this is that we make very simplified cell walls made out of lipids. They are called vesicles. So these cell mimetic structures, into them we then put these proteins, these aquaporins. These are relatively fragile parts, you can say, or entities. So in order to increase them and their stability, we have developed a technique which is similar to what you find in algae. So some algae has a tough shell made out of silicon oxide, which is the main part of sand or glass. So we have developed a technology where we can stabilize these cell mimetic structures having these aquaporins with silicon oxide. And we can make them into powders and into membranes. And by doing so, we can keep the functionality of the protein. So remember, this protein only allows water to penetrate through. So this would be a perfect osmotic membrane. So it can be used, for instance, for desalination of seawater into fresh drinking water. And this is exactly what we would like to achieve with these materials. Because if you compare such a material with the existing osmotic membranes, the big difference here is the energy used or the energy consumption by pressing water through the membrane. You only need 1% of the energy needed of today's reverse osmotic membranes with this new technology. So you can gain a lot of energy, and since the energy part of this is the main driver of the cost for desalination, this might be a disruptive technology in that sense. So based on this material, we have created a company called Accommodate, and here you can see the team of Accommodate. So Accommodate is looking at finding collaborations and partners where we can utilize these aquaporins in a stable fashion. And we are located here in Gothenburg together with Chalmers Ventures. And we are addressing this big issue and challenges concerning water. Okay, so to summarize a little bit about what I have been presenting and illustrating through these 3 different examples. So we have some common nominators here. So we started with the bioinspiration. So what can we learn from nature? And how can we use this in our best abilities in the lab in order to make new types of materials? And these materials can then be used to produce what we can say is innovations. Innovations. All right? And these innovations will through startups. So we make startup companies. And these startup companies can then utilize these ideas and these innovations to make use of and utilize it in our society. And all these together, we put all these together, we can then find solutions to maybe our greatest global challenges. So many things comes together here in once. So with this, I would like to thank you for your attention, and I also would like to thank everybody that are involved in my work and in our work here in the research groups and in the various startup companies, and Chalmers for helping out and be so positive when it comes to innovations and entrepreneurships. So with this, I'm happy to take any questions. Thank you.